Humans, we also make uric acid from purines. Our protein is degraded into urea. So we do some of this physiology as well. Now, uric acid is an interesting molecule because it can be broken down into allantoin in two different ways. Enzymatically, by urate oxidase, and it's also a really good antioxidant. So in our own circulation, uric acid is the primary antioxidant. It is responsible for about 60% of the antioxidant activity in our blood. And when we suffer from infections, we raise the uric acid levels in our circulation. So we were kind of surprised that when flies get sick, they crank up the expression of this gene urate oxidase, which should clear uric acid. And we've tested this by RT-PCR. We find that the difference between unmanipulated and infected flies is that infected flies induce urate oxidase about 12-fold higher than do wild-type flies. And we've taken mutant flies that lack this enzyme and asked what happens. We see that, and we measure uric acid levels during the course of an infection. We can see that in a wild-type fly, the uric acid levels drop by about 50% during the course of an infection, and they don't change in a mutant. Okay, so what we think that tells us is that the uric acid is being degraded into allantoin through this enzymatic route, and not through the free radical route. Okay. And it turns out that the uric acid levels start lower in these animals, and that's something we have to deal with when we're thinking about this. So what could this be doing to the animal? So normally in our bodies, in flies' bodies, we're making reactive oxygen all the time. The idea is that in the absence of infection, uric acid could be absorbing these free radicals. And if you were to infect the animal when there's a high level of uric acid, we'd expect that you might not kill the bacteria. So this puzzled us because at first we were thinking, when you have an infection, you're going to turn on a reactive oxygen response. It seems like you should have high levels of reactive oxygen inhibitors because that would protect the body. But it also protects the microbe. And so what we think happens is that during an infection, the fly flushes out the circulating uric acid, which turns out to be bad for the microorganisms, so that it reveals it to the uric acid response, to the reactive oxygen response. But different things will happen depending on what you infect it with. So we predict that if you use a organism that's resistant to uric acid, resistant to reactive oxygen, you'll end up damaging the body and not the microbe very much. Okay. So we do this with listeria, and we find the following thing. We find that we've done this experiment 5 times now. The change isn't huge, but it's always significant to less than P is less than 0.001. The mutant flies live longer than do wild-type flies. And listeria grows better in the mutant flies. So if we plot this on our tolerance curve, backwards. What we think is going on is that we're shifting from this position up into this corner here, where the pathogen load increases and health increases. So both the microbe and the host are doing better. Okay? And of course, we should have stopped there because that's what we had predicted would happen. When we went on and tested more microorganisms, we found that most of them did something different. What we found is indicated by Francisella here. In this case, again, the flies live longer when they're infected as the mutant fly compared to the wild-type fly. But the bacteria don't do as well. And so now we had trouble explaining this. We had this great explanation for why the bacteria would grow better when we had high levels of uric acid. Now we have high levels of uric acid, and the bacteria are doing worse. So we have some preliminary data saying what's going on. I'll show you what we think is going on. So I'll summarize the story. So what we think is happening here with these other microbes is that instead of shifting up into this corner, they're shifting up into this corner here, where you get higher survival and lower pathogen load. And so our explanation for this is that when you have an immune response, you've got several different immune responses that can act on your microorganisms. And there are always feedback responses that turn the immune response off. At a constant level of uric acid, this feedback is going to be off. What we suggest is happening is that when you have high uric acid levels, it prevents reactive oxygen damage to the body of the fly. This reduces feedback. You actually end up with stronger immune responses. And so the reason you end up with better killing is that you've protected the animal from the infection with the antioxidant, and you've increased the amount of antimicrobials that you're making. And our preliminary results is this is what's going on. You can actually make a higher antimicrobial response when you have a high level of antioxidants present. We're trying to reproduce this by just feeding our flies antioxidants and see if we can reproduce this by giving them vitamin C or something like this. Okay. So the last bit I wanted to talk about is the reason Umberto invited me here. And I want to mention it because we published this 3 years ago, and we're still having trouble figuring out the mechanism. But it comes from the way that we do experiments. When we infect flies, typically what we do is we take the adult fly, we infect it, and we ask what happens. And this is a really artificial view of the life of the fly, because we imagine here that it's just seeing this microbial insult once during its life. But we know that in the life of the fly, it's going to see many microbes over the course of its life. And its experience with these microbes is going to change the way its immune response works. Okay. And I'll just show you one thing. So we call this priming in the fly to avoid running into the word adaptation or memory. Flies live, after we infect flies, after we poke flies with a needle, they live for just about a month. So talking about long-term immune responses, we can get into trouble with this because a month might not be really long-term. It's the life of the fly. It's a long time for a fly, but it's not a long time in terms of survival. But what we find is that if we take the fly and inject dead microbes into it, any of a variety of Streptococcus or Staphylococcus strains shown here. So each of these have been injected with a different dead microbe. Then we come back and we infect all the flies with Streptococcus pneumoniae. We find that the flies that were previously challenged with dead strep pneumoniae survive far longer than do the other flies. These other strains are really pretty similar. So they're introducing grossly similar immune responses, but we see some real specificity to the system. And so what we're trying to do now is figure out how you can have this long-term specific priming response in flies. And we're, like I said, I have a student who's still working on the mechanism, and we don't know how this works. But just to summarize what this looks like, we think that when you have an infection, the first time you'll have a response here. What happens the second time you see a microbe? So if we're looking in this system, we see increased resistance. So the second time we get a response, we find a lower pathogen load. I haven't shown you that, but we published this. You see a lower pathogen load, and the fly survives better. Okay? So it's priming by resistance. We think, and actually we've seen, that you can also get tolerance priming. So if we take flies and feed them a little bit, a sublethal dose of paraquat, and then come back and infect them with listeria, they survive longer, and that lasts for a long time as well. So we think that you can prime either by increasing resistance or by tolerance. And you might say, this doesn't have any relationship to human biology. Malaria works this way. So if an infant is infected with malaria, the first time she gets very, very sick. The second time she's infected with malaria, she'll have exactly the same titer of parasites in her, but she won't be nearly as sick as she was the first time. So when she develops an immune response, first she increases her tolerance, and eventually she increases her resistance. And this could be a reason we have trouble making anti-malaria vaccines, because we try to go here. But that's not what we need to do. We need to reduce the power of the infection. We need to increase the health. And so the point of all of this is that there are two ways of increasing your health when you're infected. One is to get rid of the microorganism. But you don't just have to do that. You can also increase the health through other methods, and that's something I think immunologists should consider as well. So some of